Hometown hero, Mauro Toscano from LambdaClass, going to be speaking about security and diversity in VMs.
Well, hello everyone, I'm Mauro Toscano, part of the Department of Ethereum Alignment, or so says my hat, and LambdaClass and Align. And I'm going to talk a little bit about security in VMs. I'm not going to focus on the cryptography part. I think like Arantxa already did a good job there, and there will probably be more speakers that will focus on that. But I want to show you a little bit how a VM works and what can be exploited. So the VMs are very complex machines to prove. Like we have at least three kinds of proofs in our VMs. We prove like what we call like the base layers, then we compress them with stars protocol, then we further compress it with ECC protocols. And inside of each proof, we have arithmetization, circuits, IOPs, polynomial commitment schemes. We use a protocol that is called Fiat-Shamir, and we have lookup arguments. So a lot of pieces, and an attacker only needs to break one, and all the system collapses. If Fiat-Shamir is wrong, everything collapses. If arithmetization is wrong, everything collapses. So we need to be very sure that everything is really, really fine. So the other important thing is that, okay, we have a complex prover that does a good job, but we also need to decide what to prove. And what we are interested in proving is an Ethereum execution client. Right now, there are two alternatives, and there are more teams working on more, is Red or Etrex. And this means that we have around 35,000 lines of code that should be very, very well written. We have 60 direct dependencies and over 250 transitive dependencies. And when you convert this to assembly, to a compiler, now we have to prove around 700,000 lines of assembly. And that's what we are proving. And these 700,000 lines of assembly, they need to be, once again, very, very fine, very well written, and have no bugs. If there is a bug, then we are in a big problem. So, of course, like when we want to attack a VM, or when an attacker wants to attack a VM, we will have classical attacks. Like if the provers fail with an input, like this will lead to a denial of service. And if enough provers fail, like we could halt a network, and that's not very good. We could try to compromise, or an opponent could try to compromise the machines running the verifiers. That's probably another big problem. But that's on the classical side. You probably know that already. In CK, we also care about two specific types. We call it completeness and soundness. That means that we have a problem also if a user cannot prove a statement that is true. For example, they cannot prove that they own their own wallet. And the worst thing is a soundness bug. That, let's say, I can prove that I'm Satoshi. You probably won't believe me if I say that, and you will be right in not believing me. But if there is a bug, we might be able. What we are usually focusing is more on the white hat hacking, and this is going to be a duel of knights. Right? We will create papers, and we will say, okay, your arithmetization circuit is wrong, your Fiat-Shamir is wrong, maybe everything is okay, maybe a crypto analyst will say you don't have enough bits of security, and I can break this. But I will argue that we also need to take care with black hat techniques. Like, because, for example, let's say that we have a VM that is not fully compliant, and it has like 250 dependencies and a compiler. So can an opponent craft a payload that only affects your VM? Maybe they can. And of those 250 dependencies, many have one maintainer, and they are all in our code. They are all in the code we are proving. Is something to be aware of. In particular, when the VMs are not compliant and code that works on all machines fail in the CK VMs. Because, of course, the developers of those libraries, they don't know about CK VMs. What can we do? What can we do to make safer systems? I'm a big proponent that the way to make safer systems is just to add redundancy. We need to assume that things will get broken, that our prover is broken, that the guest program is broken, that everything is broken. So what do? We add more checks. We add more provers. We say, OK, we have 5 provers, 7 provers, 8 provers. They need to agree. If they don't agree, I'm going to start suspecting that something went wrong. One of the key problems that we still have is like, OK, we have like around 10 provers, maybe some in progress, some more developed, some less developed. They are all proving the same execution client. That's probably not good. Like there is a single point of failure shared between all the prover clients. And also, many use the same cryptographic libraries, so if there is a bug in the start protocol, everything collapses too. And even the compiler, one could argue that it might make sense to be careful about the compiler. So that's, for me, always like the right solution, is to have redundancy. But, of course, it's important to have robust code, and there are some good efforts and some amazing efforts on formal verification, in particular of the VMs. Which is straightforward in the verifiers. I haven't read much about how to do it with the guest programs and all these lines of assembly. Maybe someone knows more. It seems like something worth exploring. Of course, fuzzing might help us to try to find inputs that makes the programs crash. The last thing is, I think we should all strive to have more people watching the code. Like, teach more people. Let's try to not be close, because like if only two people or 5 know how something works, it's very hard to find a bug. Maybe, for someone who is in the audience, you don't have time to start reverse engineering everything and see if it is fine. So we should make an effort for people to not have to spend a year to understand what's going on and just take a look and say, OK, this seems reasonable or not. Then write simple code. I think that's something we focus a lot, but try to write simple code. Don't be fancy. Make things as simple as possible. And as I said before, like, be compliant with specs. Like, I know that sometimes we can get an advantage if we don't comply with specs, but it starts adding like degrees of freedom. Now you need to think, OK, like this should be fine, but actually we are not fully following specs, so maybe there is something that can be done. OK, that's the end of my presentation. I hope you like it. Yeah, we need to be very serious about this. Ethereum is the most important financial system for the world. Like we have millions and millions of money on it. We need to make sure that everything is really, really safe and secure. Any questions?
Yeah, we have a couple of questions from the audience. So, which part of the ZK VM stack or library is used in the project the most, i.e., what brings the most fragility?
Yes. As I said, I think like right now, the part that is everywhere is the execution client. The execution client seems to me like the first shared thing that everyone is using. Everyone is using Red. Leaving aside our vendor that they have their own. So that's probably the first thing to start decentralizing a little bit. The second thing is probably the Plunky 3, that is amazing, but I think like many projects are using it. Yes.
The last question is, how many verifiers for the provers are going to be embedded in the clients? WASM verifier, EVM verifier?
I think that's more a question that we should ask as a community. I don't have an answer. The more verifiers, the better, from the point of sense of soundness, not from the point of sense of completeness and denial of service attack. Because if I require 10 out of 10 CK provers and I can shut down one, then the system doesn't advance. So we will need to discuss trade-offs. I think like right now is where we are. The Ethereum Foundation has been thinking of something about 5 out of 8. So that's probably a good number.
Thank you very much.
Thank you, everyone.